Hey there, and good morning to you, chemistry team. It's your chemistry coach coming at you with video number 3 for our coordination compounds complex ion chapter. For us, that's chapter 24. We're skipping around a little bit, but I want to get some of these later chapters to talk about the equilibrium for all different kinds of species so we can do our equilibrium reactions lab later, which takes all of that. It's like a big buffet of equilibrium, just putting it all in there and mixing it all up and seeing how they all interact with each other. So we looked at nomenclature for complex ions, what they are, how to name them, how to figure out oxidation numbers, essential metal ions, ligands, whatever you want to call them. Today we're going to look at what's important. This is put a little star next to this video, hashtag it, mark it with a red flag, whatever you got to do. This is going to be a key video for your equilibrium reactions lab because we're going to be looking at the different types of reactions that complex ions can undergo. You're going to be quite amazed at the impact of these that have been lurking in the background we didn't even know about up until this particular semester. So we're going to look at acid-base behavior. We're going to look at how they interact with precipitates. Can we take precipitates and dissolve them by adding ligands? What could we do here? I'm not going to do everything in the particular textbook, just enough to get us going into our equilibrium reactions lab. So I'm going to start with acid-base behavior and reactions of complex ions. We'll start easy and then we'll get a little more complicated. I recommend that you review the video from, I think it was chapter 15, when we introduced equilibria, kind of in the beginning, when we manipulate equations. If you turn an equilibrium equation backwards, right, you do 1 over the k value. If you multiply it by 2, you square the k value. And we can use Hess's law to add those together, all right? And when you add 2 or 3 equations together, then the overall k value is k1 times k2 times k3. I highly recommend you review that video because it's going to help you when we do this. We're going to apply those concepts to a lot of fun stuff with complex ions. All right, so I'm going to do this in 2 parts. We're going to look at something that was kind of weird that, people would find that just metals, right? You do like a iron 3 nitrate solution and find out it's slightly acidic. And they're like, what? Because we know nitrate ions are neutral, so how the heck could an iron 3 cation be acidic? Why would that make an acidic solution? We would expect it to be neutral. And lots of other highly charged small cations tended to be a little more acidic than we thought. And when you look at it from a complex ion point of view, metals, right? We always write just Fe3 plus or Al3 plus or zinc 2 plus AQ, but you got to remember that AQ means it actually has waters as ligands attached to it, right? It's hard to predict. We're not going to be able to predict how many waters. We don't have that on our coordination number table, but usually we'll put like an N or an X here. It's like, I don't know how many waters. There's just a bunch of waters. But it's such a pain to write that we just write Fe plus 3 aqueous with the assumption that it's got all those water ligands attached to it. Let's take a look at what's actually happening in solution. Let's say, for example, that this iron 3 ion actually has 6 water molecules because you got lone pairs on those oxygen atoms that can connect in, right? Let's say we had 6 of them here. This would form an octahedral shape, right? You have 6 attached to it, so those water ligands are octahedrally organized around there. But it's in solution, so there's the solvent, right? Well, think about kind of like water autoionization. Can a water molecule donate an H plus to another water molecule? Not super favorable, but that can happen again. One of these water molecules can donate an H plus over to that oxygen, forming the hydronium ion, and then one of those 6 waters becomes a hydroxide or hydroxo ligand with a negative charge. So the positive free charge, because waters are neutral and the iron's a plus 3, now you've got the 5 leftover neutral water molecules and an OH minus, so that OH minus and the Fe3 plus gives you an overall 2 plus. Right? That actually has a Ka value of 9 times 10 to the minus 4. I think that's even a stronger acid than like acetic acid. That's like 10 to minus fifth range. Whoa, that's kind of weird. Some of these hydrated metal ions can function as weak acids. Now this actually would be Ka1 because we've got 5 water molecules. Couldn't we come down and do that again? And then have 4 waters and 2 hydroxides and a +1 charge, you get a Ka2, a Ka3, but it gets weaker and weaker as we go. But I just want to give you a rough idea that a lot of these, and it turns out the more highly charged it is, and the smaller it is, so the higher the charge density, the stronger that acidic behavior. But so don't be surprised when you see some metal ions, hydrated metal ions in solution being acidic. Weird, huh? So I drew it because we talked about the geometry. Two coordination numbers is linear. You could have tetrahedral, square planar, all those kinds of things, but I didn't show it to you. So I figured I'd have some board space. Let's go ahead and show it. So if we have the 6 water ligands, right, they attach as an octahedron. So you got one up, one down, and then you got that square around it, 90-degree bond angles everywhere. This is octahedral, okay? But what happens, since that iron is super highly charged and small, it has a high charge density, it's pulling electron density away. If you remember, we looked at acid-base theory. That weakens this bond right here, makes it easier for this hydrogen to pop off, right? Because that iron's really, so an iron 2 wouldn't do it, it would do it a little bit, but not as much as an iron 3. So it's weakening this bond right here. And then that can pop off, attach to that water molecule, and leaves you with the OH minus ligand right there, and then the 5 waters. Still octahedral in that case. But I just kind of wanted to show you what that actually looked like from a geometrical perspective. We don't have a lot of that on homeworks and things, but it's nice to see every once in a while. So that's kind of a basic start to it. Let's take a look at what if a complex ion has ligands that are acidic or basic. Could we destroy that complex ion? If it has, say, basic ligands, could we add an acid to it and just explode that complex ion? Or if it has acidic ligands, could we add a base and blow that baby up? Yes, we can. We'll be right back. All right, it's going to get a little bit more challenging for this one. We got to think a little more about principal species or predominant species, how things exist. Their dominant forms, dominant ions in solution. So let's just attack it with a problem and show you how to solve it. We're going to be doing this thinking process a lot. Doesn't matter what we apply it to, but you're going to apply this process when we do combinations of equilibrium reactions. All right. So let's say we've got a complex ion. What's that? The tetrahydroxo zincate. Zincate 2, something like that, ion. I think so, right? It's an anion, so we got to go to the zincate. Can that complex ion, regardless of its weird name, be destroyed by adding 0.1 molar nitric acid? So the 0.1 molar isn't too critical in this scenario. Let's break this down, right? So this is a complex ion. That's going to be existing in equilibrium with its metal ion and its ligands, right? That's a strong acid. So let's take a look at what this strong acid has. First thing I want to do is, does the strong acid have anything in common with this? Let's look at this. So this is a strong acid. So that will exist as the hydronium and the nitrate ion. Right, 100%, right? There is no HNO. There are no HNO3 molecules in solution. It's all hydronium ions and nitrate ions. Now let's take this and write its equilibrium equation. So let's bring this down and write its equilibrium equation. So we've got the zinc tetrahydroxo, and let's do the equilibrium, right? Because all complex ions, all solids, all weak acids and weak bases exist in an equilibrium. So that's going to be an equilibrium between its central metal and the 4 hydroxides. Let's call this equation 1. Ooh, dropped my pen. Let's call that equation 1. That's our starting point. That's our equilibrium. And then we jack in some nitric acid, right? First thing I'm going to look for is, common ions, things that can happen. There's no zinc or OH minus in there, right? I'm not worried about that. Something else I'm going to think about is, could that nitrate ion form a complex ion with the zinc? All right. And you'd have to look on your table, right? And if you look on your coordination number table, see the ligands? There's no NO3 minus in there. Nitrate can't, right? Nitrite can, but nitrate doesn't act as a ligand. So I don't have to worry about this. Plus, that would have to be a higher concentration, right? Because remember, you need 4, 5, 6 molar or above to form a complex ion. So that's a really low concentration of that acid. So I'm not worried about this nitrate. Let's look at these combinations here. Let's do it in blue. I'm not worried about that nitrate reacting with that zinc. That nitrate ion is not going to react with the zinc. Could the nitrate ion react with the hydroxide? Well, that's negative, so that's probably not going to happen. You see the combinations I'm doing? So I'll look at these species I'm adding and look at the two species in the equilibrium, look for possible reactions. So the nitrate's not going to react with the zinc. You know, could that form a precipitate with the zinc maybe? Well, nitrate ions don't form precipitates. Okay, so we're good there. So you got to check and see, can that anion from the acid form a complex ion or a precipitate with that zinc? Now, the anions won't react, right? The cations probably won't react, right? The hydronium ion and the zinc 2, they're both positive cations. They're going to repel each other, right? But if you look at this combination here, ooh, do you see that? You see the hydronium ion from the strong acid, from the nitric acid, and the OH minus ion from the complex ion, the ligand? Those are going to react in an acid-base reaction. So this will come down in equation 2. This is the thinking process. Take a look at the two species in the equilibria here on the right side. Look at the species you add. Look at every combination. Check for precipitation formation, new complex ion formation, and acid-base reactions. You can get a lot of combinations. Can you see this? Oh, something smells good in the house. I wonder if that's bacon. All right, here we go. Let's do our second equation. I'll do that in green. So I'm going to bring this OH minus down. There's the hydroxide ion from the equilibrium of the complex ion. That's going to react with the hydronium ion from the strong acid. Hey, what are we going to get here? What are we going to get here? We're going to get 2 water molecules. Okay, we're going to get 2 water molecules from that. Well, let's think about this. Let's add those two equations together, right? Use our manipulation techniques, right? Take a look at what those equations are, how they're manipulated, those kinds of things. If you look at that, do you see the 2 water molecules on this side? This is the reverse of the water autoionization of water, right? It's the reverse of the autoionization of water, which means it has a K value of 1 over Kw. So let's take a look at this. Let's do this in black. So this, let's look at K1. What is K1? This is a complex ion breaking apart. Now, Kf is the formation of a complex ion, correct? So this is the reverse of this. So this is 1 over the Kf value, right? Because it's backwards. Forming a complex ion is your Kf value. This is the reverse of that. And we could look up the value of Kf for this and just go 1 over that. This is the reverse of water autoionization. So let's look at K2. That is 1 over Kw, right? It's 1 over Kw. When we add these together, I'm going to add those together. We want to get rid of the species they have in common. See the OH minus here? When I add these two equations together, I want that to go away when I add them together. Notice we have 4 of them up here in equation 1, but only 1 of them down here in equation 2. So if we multiply equation 2 by 4, let's do that. Let's put this in brackets. And let's multiply this by 4. That would give me 4 OH minuses. So if I have 4 OH minuses on the left and 4 OH minuses on the right, they're going to cancel out. So we want to cancel out the like species. That's the goal when we add these two equations together. So if I multiply that by 4, then I have to put that to the 4th power, right? Oh, so I took the original autoionization of water, reversed it, and multiplied it by 4. So I'm going to take the inverse of Kw, because I reversed it, and raise it to the 4th power because I multiplied it by 4. This is the reverse of the formation of that complex ion, so the K value for that equation is 1 over the original Kf value. Got to get good at manipulating things. Let's add these together. You ready? Let's get the overall equation when we add these babies together. All right, so I didn't multiply the first one by anything, so I'm just going to keep the original complex ion. All right, that stays. The OH minus will disappear. I'm going to get 4 hydronium ions. You see that? Because I multiplied by 4, so I'm going to get 4 of these, and 8 of those. Everybody see that? 4 of those, and 8 of those. Everybody see it? And that's everything on the left-hand side, because this is going to go away. And that's going to go away when you add them together. So I'm going to get the original complex ion plus 4 hydronium ions, giving me the zinc ion. I didn't multiply this by anything, so I'm going to get the zinc ion. The hydroxide ions are gone. That was the whole point of adding them together. And I'm going to get 2 times 4, which is 8 waters. All right? I'm always looking for that overall equation. Now what we want to do, does this equation happen? Now remember, if products are dominant, K is bigger than 1. If reactants are dominant, K is less than 1. So what we need to do now, this is part 1 of this. Now we want to calculate the K value for this and look and see if that's bigger than 1 or less than 1. If it's bigger than 1, it's going to be product dominant. And yes, this acid can destroy that complex ion because it's going to mostly exist as these. If K is less than 1, it's going to mostly reside as the complex ion. So we'd say, nah, it's probably not going to, not to a great extent. So we need the overall K value. So I'm going to erase part of this, and do me a favor, pause the video, look up the Kf value for this complex ion, the tetrahydroxyzincate 2 ion. Go find the Kw value. And remember, if we're taking and adding these together, the overall K value will be K1 times K2. Well, there's your K1, there's your K2. Do it and see what you get. It's going to take a lot of gymnastics on your calculator. There's a lot of crazy exponential stuff. So pop that out for me real quick. All right, have you done it? Have you done it? So remember our rules. If we're adding these two equations together, we multiply the K value. So what's K1? It's the inverse of the formation constant for that. We can look that up. Right? K2 is the inverse of the autoionization of water to the 4th power. Or you could go Kf to the minus 1 times Kw to the minus 4. You could go like this. We'll do it this way. I don't care, right? If you want to write it like this, or if you want to write it like that, it's the same thing mathematically. It's up to you. Let's go look those values up. All right, let's look up the Kf value. So I'm going to look for my formation constant, and this is the tetrahydroxozinc. So zinc's probably towards the bottom there. So here's our formation constants. Let's look up zinc. Do you see the tetrahydroxozinc Zincate 2 ion, 4.6. Whoop, where is it? Yep, 4.6 times 10 to the 17th. Did everybody see that? 4.6 times 10 to the 17th. Let's write that in. 4.6 times 10 to the 17th. We know kW is 1.00 times 10 to the minus 14th. Raise that to the 4th power, so we got 2 significant digits there. You could have gone 1.0 there and still had 2. So punch those numbers in, go to 2 significant figures. I get 2.173. 2.173. You might have to try this a few times. Times 10 to the 38th. What? That's huge. That's huge. So that's going to round up to 2.2 times 10 to the 38th. So that is the K overall that I got, the K overall. Do you think that's bigger than 1? Right? A lot of times they'll use a kind of a guideline of 10 to the 10th. Any K value bigger than 10 to the 10th is pretty much all products, right? So since this K value is bigger than 1, let's go K is way bigger than 1. This is product favored. Right? K is way bigger than 1. That's product favored. So I would say yes to this question. Can this complex ion be destroyed by adding the 0.1 molar nitric acid? Heck yeah. For sure, for sure, for sure. It's a goner. That's way huge. If that had been like 1.5 times 10 to minus 15th, I'd say no, it wouldn't. It's going to be almost all reactants in that scenario. Let's do one more. I'm going to just put it up on the board. You attack it, see how you do. And then in a separate video, we'll look at the precipitation reactions of these. Right? It's a special way of thinking. You got to do enough of them to get used to the rules of the game. Once you do, they become pretty easy. So I'll erase this board and put another one up. Hi guys, you like my new mask? My 13-year-old daughter is pretty much almost you could consider a professional seamstress. So she runs a business making different things. So she decided to take some of her extra fabric and make, because we can't get a hold of these darn things, so she made me a money one. She made me a whole bunch of like little things for change or leftover dollar bills. You know, you can just stick it in there with zippers, the little money pouches. So I said, hey, we can't get a hold of these stupid things. So she made everybody in the family one. I got my money one. Yay! All right, anyway, I can't breathe very well. So cute. Talents. It's good to have practical talents. All right, here we go. Here's your question. You ready? Similar to you do the exact same process we did last time. Can the tetraamine zinc 2 ion, since that's a cation, we won't do the ATE. So the tetraamine zinc 2 ion be destroyed by adding the same thing, 0.1 molar nitric acid, right? So again, what does the nitric acid consist of? Write the equilibrium reaction for that complex ion, right? Because we're starting with it. We're not forming it. We already start with it, right? So your first equation will be the reverse of the formation of that complex ion, 1 over Kf. And then take a look at the 2 species of that strong acid. Can they react with any of those species in that equilibria with the complex ion through an acid-base reaction, neutralization, formation of a precipitate, or formation of a new complex ion? Give it a shot. I'll write a couple equations up on the board there. All right, so I popped up the first equation for you. You always start with that. Take the species provided, whether that's a solid or a weak acid, weak base, or complex ion. Start with it and draw its equilibrium, all right? So I'm starting with equation 1, which is the reverse of the formation of that. So K1 is 1 over Kf. Let's take a look at what we're adding to it. Again, this is a strong acid. So we're going to have hydronium and nitrate. So we're adding 2 species to the mix. We have these 2 species there. We're adding 2 species to the mix. We got 4 species. Oh, look at all the possible combinations. So we got 4 possible combinations, right? So what could happen? That's a possible combination. That's a possible combination, right? The hydronium ion with the zinc ion, the nitrate ion with the ammonia. That's because the ammonia is the ligand here. Or the hydronium ion with the ammonia, or the nitrate with the zinc. Do you see the 4 combinations? So 1, 2, 3, 4. Look at all 4 combinations and just go through a process of elimination, right? One of them's definitely going to go, maybe even 2, more complicated. Now, I know that the cation hydronium and the cation zinc aren't going to happen. So I'm going to eliminate that first possibility, the 2 cations. Let's take a look at the nitrate, right, with the zinc. Now, again, we talked about last time, nitrate is soluble. It's not going to form a precipitate with that, and it cannot function as a ligand. So I'm going to ixnay that one. So the nitrates do nothing. That's why we love nitrates. They don't do anything. Let's look at these combinations. We got the hydronium ion with the ammonia, but the ammonia is a weak base, right? That has a Kb value. Couldn't the hydronium ion attack that weak base? Yes. And then we got to look at the nitrate ion with the ammonia. Well, nitrate doesn't do anything, so I can eliminate this. So the hydronium ion can react with that. Now, the last problem, we had hydroxide there, the stronger base. Now we have the weak base. So we're not going to get the autoionization of water here. We're going to get the reverse of this. Take a look. So let's bring this equation down. Let's do this in blue. So equation 2, that's a really big 2. I'll do it in black. That will be the ammonia, right? Because that ligand is a weak base. If that ligand has basic behavior, it can be attacked by an acid. If that has acidic behavior, it can be attacked by a base. And your second equation will be a neutralization reaction, right? If you could form a precipitate with the anion with that cation, your second equation would be a precipitation reaction. If that could form a complex ion, it would be you could have 2 complex ion reactions. We'll do that in the next video. It gets crazy. All right, so let's add these together. So we're going to get an acid-base reaction going on to get the ammonium ion plus water. Right? So we're always going to get water in the neutralization part of it. Let's take a look at what K2 is. All right? Now, we can't call that Kb because Kb would be the base plus water forming OH minus. So that's not Kb of ammonia. This is ammonia getting attacked by an acid. All right? There's no solid in there, so it's not a KSP. There's no complex ion, so there's no Kf, right? I don't see 2 water molecules reacting with each other, so it's not a Kw. So what could it be? The only thing left, if it's not a Kb, it's not a KSP, it's not a Kf, it's not a Kw, either backwards or forwards, it must be a Ka. You see the hydronium? Remember, a Ka is something reacting with water to form hydronium. This is the reverse of the ammonium ion acting as an acid. You see that? So this is 1 over Ka for the ammonium ion. Whoa, that's getting crazy. So what we can do now is add these 2 equations together, get rid of the species they have in common. Do you see the 4 ammonias here? See that 4? So I need to multiply this equation by 4. So let's put this in brackets. Let's multiply this by 4 to get the 4 ammonias on both sides. So I'm going to put this in parentheses and raise that to the 4th power. This is the reverse of the ammonium ion acting as an acid multiplied by 4. So I'm going to raise that to the 4th power. So let's add these 2 equations together. Let's get the overall equation. And then once we have the overall equation, we'll calculate the overall K value and see if it's bigger than 1 or smaller than 1. All right, what's my overall equation here? Ooh, let's use this purple here. So I've got the original complex ion The ammonias go bye-bye, right? Because I'm going to have 4 on the left, 4 on the right. I'm going to get 4 times 1, which is 4 hydronium ions. Similar setup to the last problem. I'm going to get the zinc ion. I'm going to get 4 times 1 is 4 of the ammonium ions. And then 4 times 1 is 4 waters. I ran out of board space. There is my overall equation. So what is K overall? Calculate that for me. So that's going to be K1 times K2, which is 1 over the formation constant of this. Look it up on your table. 1 over the Ka value for that. Go figure that out for me. And we'll pop it up on the next board. We'll be done with this video. And let's see if that's K's bigger than 1 or smaller than 1. All right. I don't know how far you got. Some of you probably got stuck right here. All right. So we're getting K overall. So we're going to take equation 1 times equation 2. Equation 1 is the reverse of the Kf value for the tetraamine zinc 2 ion. So let's look that up. Let's get our Kf table. Let's look down to the zinc with the 4 ammonias. So this is the tetraamine zinc 2 ion. That's 4.1 times 10 to the 8th. 4.1 times 10 to the 8th. Let's write that down. So I'm going to go 1 over that in my equation. Now let's look up the Ka value for the ammonium ion. Remember, the second equation is the reverse of that. So let's look at our Ka table. Here's our Ka table, right? So look for the ammonium ion. And it's not there! Oh no, it's not on there! Do you remember what you do if you don't find it? Remember, Kw is Ka times Kb. So Ka for the ammonium ion is Kw over Kb for its conjugate base. Ah, how soon we forget. Remember that? So that comes from Kw is Ka times Kb, right? So the Ka for that will be the Kw over the Kb of its conjugate base. So this will be 1.00 times 10 to the minus 14th. Let's look up the Kb value for ammonia. So get your Kb table. Look up ammonia right on the top. Do you see the 1.8 times 10 to the negative fifth? 1.8 times 10 to minus fifth? We should be able to bang that out now, okay? So I want you to solve for that and then solve for K overall for me. I'll give you a minute or two to do that. Have at it. Did you get what I got? All right, so I'm going to plug these values in. So K1 will be 1 over Kf, or 1 over 4.1 times 10 to the 8th from the table. K2 is 1 over the Ka of the ammonium ion to the 4th power. So we solve for Ka. So I got 5.555 times 10 to the minus 10th. Good to 2 significant figures for the Ka value, right? Took the Kw divided by Kb. That's what I got. So I'm going to plug in 1 over 5.555 times 10 to the minus 10. Raise that to the 4th power. 2 significant digits, 2 significant digits. I end up getting 2.561 times 10 to the 28th. Good to 2 sig figs. Rounds up to 2.6 times 10 to the 28th. That's way bigger than 1, guys. K's way bigger than 1. That is product favored. So to answer this question, can the tetraamine zinc 2 ion be destroyed by the nitric acid? Heck yeah! Let's do a whole nother video, but let's throw solids into the buffet.